Let's take a look at our next bug. Here, we have a very interesting piece of code. We want to play some games, but we don't want to play the games manually. We want to play the games using some automated solvers. So we have a framework that allows us to define games that we can play, as well as automated solvers that can solve that game. In the case of this code, just simple word games. We're giving the user the ability to evaluate the effectiveness of these solvers by registering new solvers and seeing whether or not they play the game more effectively or not. As part of writing this code, we think about making some innocuous changes to this code, maybe moving a couple of lines around, and when we do that, we get a bug, we get a name error. Let me show you the code, then let me run it, and I'll show you how the bug pops up, and we'll see, can you spot the bug? There's quite a bit that's going on in this code, and I'm going to remove from your view part of the elements that don't really matter. Some of this is just setup for our code itself. The main part of the code is we have some generator coroutine that implements a word game, in this case Wordle. The way this works is every time you guess something, it will check that guess against the answer and it'll tell you what the response is. Correct part of the word, but not in the correct position, not part of the word at all. Then you have some solvers, like a random solver that just randomly guesses words, and a smarter solver, something that says, you know what, I'm going to take what you told me as a response, and I'm going to figure out what the possible guest list might look like based off what you told me. So if you told me the letter W isn't in the word at all, well, I'm not going to guess anything that has letter W in it anymore. I'm going to run a bunch of different puzzles of using different words that I pull from the word list, using every solver that I have, using every game, with a differing maximum number of tries. And I'm going to see, can my random solver solve this game of Wordle in 5 tries, in 10 tries, in 100 tries, in 1,000 tries? Can my smarter solver do this? I'm going to write a little bit of code here. And as a consequence of using those generator coroutines and the generator coroutines returning a value, what I'm going to do is I'm going to repeatedly send something into my solver, get the result out of that, send it into my game, and I'm going to send these things back and forth. I'm going to have these two entities interact in that fashion. I'm going to wait for a stop iteration to occur, which indicates the game has said, I'm done, there's no more steps left, I have an answer. And I'm going to grab whether you solve the game or not from that stop iteration by looking at the e.value. That's what's returned from this generator expression, from the generator coroutine. And when we run this code, it should work, but what we'll end up seeing is this thing is going to give us let's run this without our Python hash seed. This thing is going to give us a name error. And the name error is going to be right here with this e.value, but the only way that we got to this line is if we broke out of this while true loop, and the only place we could break out of this while true loop is here, and here we create this variable e. Can you spot the bug? Now there's a lot going on in this code. And because there's a lot going on in this code, well, there might be some obscuring elements, but it turns out that this bug is actually quite straightforward. I'll give you a giant hint. Here, we have just the try except portion where an exception has been raised, here a zero division error, and we're going to look at that exception and maybe do something about it, maybe capture the e.value or whatnot. We're going to do one small thing. We're going to take whatever exception was given and we're going to assign it to another variable name, e underscore. And outside of this block, we're going to see, does that e underscore exist? Yes. Inside of this block, does the e underscore exist? Yes. Inside of this block, does the original as e variable exist? Yes. Outside of this block, does that e exist? No. That's why you got a name error here. So, what's the bug? Well, it turns out that this isn't necessarily a bug, so much as intentional behavior from the Python interpreter. One thing that you might not know is that when you do a try except, if in that except you actually capture the exception using the accept exception as syntax, there is an implicit deleting of the reference to the exception at the very end of the block. There's an implicit del e. you'll see this in the bytecode as a delete fast. And this is done intentionally because if it were the case that you didn't clear that exception within that block, well, there could be a circular reference between the exception and its traceback. And as a consequence of that circular reference, what could end up happening is you start getting a lot of memory pressure, and especially if you have a lot of exceptions, and especially if this is maybe a program that's already on the verge of something going wrong, you could easily have enough memory pressure that would lead to an out-of-memory situation. And so the Python interpreter explicitly tries to avoid this issue. And if you go to the Python documentation, it actually even details this. It's just that everybody skims past that section. And so the answer to our bug is actually quite straightforward. All we have to do is make sure that any time we're working with the actual bound value of an exception, we're either doing it exactly within this block, which is sufficient for our cases, or we're making sure to explicitly rebind it to another variable name. There we go. And so if we do this, we'll see that our solver works, and we can see a couple of results from our various solvers and our various games. It takes a moment for this to run because we have so many different trials, but you can see that our random solver has almost no possibility of actually solving a game of Wordle, even with 1,000 tries, but our smarter solver is actually quite good. And you can think that there's quite a bit of a margin here. At 10 tries, it's got a 90% chance of solving this. You only get 5 tries in the game, so maybe you could write an even smarter solver that has more than a 90% chance within 5 tries. And then, of course, you could register it with this framework. But of course, like with all of our bugs, the explanation is the important part. And for the purpose of this bug, I think that the standard library documentation really does explain what's going on here very clearly. However, what I want to share with you is not further details for the decision-making process behind this, but instead how you might discover these kind of things themselves. There are a number of cases where you might need to, as part of your debugging process, really try and figure out what is going on behind the scenes in Python. Python, at its most superficial level, appears to be an incredibly consistent language where everything just works. And that's great, especially when writing short, simple programs. But as you write larger, more complex programs and dig deeper and deeper and deeper, you realize, Python is very well designed, but like any real-world tool, there's always these small little details of things which you would think would be very easy to set up, very easy to solve, and just aren't. One that I saw just very recently is, you'd be very surprised about this, if you do something like the following. You have some object, and that object implements EQ, and in that EQ, you perform an equality against a dictionary mapping proxy. So here, let's do it like this. It should be like this. You'll actually be able to circumvent the mapping proxy mechanisms. Here, I'll do it against int, because that'll be a little bit easier. So here, we'll do this. And if you look at the type of this thing, you'll see that's a mapping proxy, or actually typically that's a mapping proxy. Now what we're going to do is we're going to make sure we have an instance of that. We have an EQ. We're going to get the other ones. Let's see if I can try it again with the list for a moment. And what we want is we'll discover that we can actually escape the mapping proxy. And so let me check one thing here. Okay, there we go. And then in order to do this, we need to pass this to EQ. So we have to make sure that this actually gets tracked. So we might have to do a little bit of playing around with the way that this thing dispatches. There we go. So you can see it's a little bit sensitive to the dispatch. Well, what this means is we can actually get the actual dictionary that supports the integer instance. So if we do something like this, d real equals 42, we can do some really weird things that we shouldn't be able to do. And I think I can do like this, and then here I can do x equals 1, 2, 3, x.real. And you can see this is very strange because y is the real component of this value, 42. And I can do some very, very bizarre things. When you go through the Python bug tracker, you'll see that this requires some very in-depth knowledge of how the Python interpreter works and why it's so difficult for them to actually fix this. And you'll see that this is one of these cases of these bugs where something that just shouldn't happen, that you wouldn't expect to happen, happens. They can't fix it. They don't want to fix it. And it requires a little bit of in-depth knowledge. Now, are you likely to run into this particular situation in practice? Probably not. But even though some of these start getting quite obscure, it is worthwhile to add to your toolkit of debugging tools, at the very minimum, the ability to look at and read Python bytecode. And so for our explanation, what I want to focus on is, what is the Python bytecode? How do you look at it, and what can you gain from it? Here, you can see the dist module. In the dist module, there's really only one major thing initially that you really need to know about, that dist function. And what that dist function is it takes some code object, some function, some class, some generator, whatever the case may be, and it tells you what is the actual code behind the scenes that will be run by the Python interpreter. If we looked at our original bug, for example, with the try except as an example, we could see the behavior quite easily. What we could see here is when we run this try except, there's a lot of additional mechanism around how the try except works, but here you can see it is storing something in this variable e, and you can see this delete fast where it does the del e, the deleting there. So you can actually see it directly in the bytecode. And in general, there's quite a few things that are useful that you can see in the bytecode itself. But I want to walk you through how you might read the bytecode, and just really strongly encourage you, take some Python code that you have, maybe not too long because this is quite verbose, and try and make sense of it. Now, note the bytecode changes a lot. And so there are certain aspects here, like if you've seen the bytecode before, you might not have seen this resume before. There's a lot of aspects that change with the versions of Python that you're using here. I'm using Python 3.11. But when you look at this bytecode output, what it's telling you is the line number of Python code. So each one of these space delimited blocks is one line of Python code. What this immediately tells you is one line of Python code can actually do a lot of work and can do a lot more than you might expect. Here, the second column is the index of the bytecode instruction. That's not generally useful for any sort of debugging. Here you can say that this load global appears to be 10 bytes in size. This binary op appears to be 12 bytes in size. This pop top appears to be 4 bytes in size. They used to be much smaller, but you can see some details here. So this is the index of the bytecode. Again, that's not particularly useful in practice. This middle column is actually very useful. This is the operation that's occurring. And I'll give you a very quick cheat sheet for the operations that you care about. Of course, you'll see things like return value. That's what a function returns. You'll see things like load, global, fast, or deref, or their equivalent stores. And this just means load a variable from the global scope, load a global from the local scope, load a variable from the global scope, the local scope, or from the closure scope, or store it back. You'll see a bunch of things like binary operations. This used to be a little bit more explicit, say binary multiply or binary addition, but this is some syntax that implements an operation of 2 arguments. You'll see things like call function. You'll see operations that operate on the Python stack, like pop top, that just throws something away, or you'll see things like rot. There's various things for like rotating. So when you have the syntax for, xy equals yx, all this, oh, that's interesting. Very interesting. Historically, this would do just a rotation operation. So the loading and the stores you wouldn't actually see. You would just see one single bytecode that did a rotation. But you can see here in this case, it's actually doing the load, and the store, and the store. So I wonder if I do it on 3, if it will dot me into a rotation bytecode. Bytecode changes all the time, so these things may change. So you can see here it doesn't. And in different circumstances, in different modes of Python. Let's try it, see if that makes a difference. No, it doesn't make any difference. You'll see this bytecode change, but it's worth looking at this. When you look at the bytecode, there's quite a few things that you can get a good sense of. For example, do you know off the top of your head, if you have some complex line of code like D, an assignment into a dictionary, and there are 2 functions involved, do you know which of those 2 functions gets run first? Well, the answer is you don't have to know ahead of time. And you shouldn't be expected to know ahead of time which of those two functions runs first. It doesn't really matter that much for you to have memorized that, but what you should know is how can I quickly answer that question for myself without having to go to Stack Overflow? And all you have to do is disassemble this line of code here, and you can see exactly what's happening. Here you can see there is a call here and a call here. You can see the call here is happening on G. The call here is happening on F. So it's very clear that G is being called before F is. And so if these happen to be two functions that for whatever reason operated on some external or global state, so here let's say return X, X will be a global variable here. You can now see why it is the case that, let's call the function. And here, you can see why it's storing 2 to 1 and not 1 to 2. Well, it's based on the order of these things. And so if you're ever curious about these details, really don't go and memorize them. Going to Stack Overflow is going to waste a lot of your time. Instead, go to the bytecode and ask the bytecode itself to tell you the answer, and you'll find that the more you do this, the more readily you can quickly eyeball that bytecode and say, oh, that's actually what's happening behind the scenes. Of course, there are certain things that you can't see from the bytecode, like, for example, if you happen to have two objects and they are part of some type that is on some derived hierarchy. So you have an X and a Y, and you do a binary operation on these, and both X and Y both implement the reversed and normal methods for this operation. Which one of these methods actually gets called? And you won't be able to see this from the bytecode at all. And the reason that you won't be able to see this from the bytecode is the bytecode's only going to tell you that it tried to do a binary operation. It's not going to tell you which of these it ended up calling. This is where you'll actually have to dig deeper into the interpreter and debug. But you can think that these cases are a little bit rarer. Being able to read through that bytecode and figure out exactly which of these is being called, and then combining that with a little bit of just regular old debugging, putting print statements, putting breakpoints, that usually gets you really, really far along the way. So for those of you who've never played with bytecode before, I really exhort you, having seen this, go take a look at the bytecode and see what kind of bugs it can help you discover in your code.